Imagine a single company in a single country controlling over 90% of the most critical resource for the 21st century. This isn't a story about oil or rare earth metals. It's about something far more fundamental to our future: the silicon engines that power artificial intelligence. In the first quarter of 2025, one American company, Nvidia, shipped a staggering 92% of all discrete graphics processing units, or GPUs, sold worldwide. Its closest competitor, AMD, was left with just 8% of the market. Intel, the titan of traditional CPUs, held a market share of 0. These GPUs have become the undisputed workhorses of the AI revolution, the essential hardware for training the large language models that are reshaping our world. So, what happens when the world's second largest economy, a nation with ambitions to lead in AI by 2030, is suddenly and decisively cut off from this critical supply? This is the story of the GPU quest, a high-stakes, state-backed scramble inside China to replace Nvidia, born not out of choice, but out of necessity. To understand China's monumental challenge, one first has to understand the kingdom it's trying to dethrone. Nvidia's dominance wasn't built on hardware alone. It was built on a software empire that took 2 decades to construct. The story begins with the evolution of the GPU itself. Originally designed as specialized accelerators for rendering graphics in video games, their architecture was fundamentally different from a CPU or central processing unit. While a CPU has a few powerful cores designed to execute tasks sequentially, one after another, a GPU has thousands of smaller, simpler cores designed to perform many calculations simultaneously, in parallel. This was perfect for rendering millions of pixels on a screen at once. But in the early 2000s, researchers and scientists began to realize this massive parallel processing power could be used for more than just games. They started applying it to general-purpose computing tasks. In 2006, a team at Nvidia, led by Ian Buck, launched a platform that would transform this nascent field into an industry. It was called CUDA. CUDA, which stands for Compute Unified Device Architecture, is more than just software. Think of it as the operating system for a GPU. Just as developers write applications for Windows or iOS, AI researchers and data scientists write their code for CUDA. It's a parallel computing platform and programming model that allows developers to unlock the power of those thousands of GPU cores using familiar, high-level languages like C++, Python, and Fortran instead of complex, low-level machine code. This unified platform was a masterstroke. It meant an application could be developed on a single GPU in a desktop workstation and then be deployed seamlessly to a massive data center, a resource-constrained embedded device, or a cloud server with minimal, if any, code changes. It created a frictionless development pipeline that was simply irresistible to the burgeoning AI community. Nvidia didn't just sell hardware, it built a kingdom. The CUDA toolkit, which is free to download, provides developers with a treasure trove of essential tools. It includes GPU-accelerated libraries for nearly every conceivable task, like Curand for high-performance random number generation and QFFT for fast Fourier transforms. It offers advanced debugging and optimization tools. And through its NGC catalog, it provides a library of pre-trained AI models that data scientists can fine-tune, saving them enormous amounts of time and resources. This comprehensive offering created a powerful network effect. The more developers who adopted CUDA, the more tools and libraries were created for it, which in turn attracted even more developers. This virtuous cycle has resulted in an ecosystem of over 30 million developers, with deep partnerships that embed Nvidia's tools into the core workflows of tech giants like Microsoft, Oracle, and Amazon. This has created what analysts call ecosystem lock-in. As one report bluntly puts it, developers are trapped in Nvidia's stack. Switching to a competitor, like AMD's ROCm or Intel's One API, is not a simple software update. It's a monumental undertaking that requires rewriting vast amounts of code, retraining entire engineering teams, and sacrificing years of accumulated performance optimizations, a cost and risk that few organizations are willing to bear. You might be wondering, why is this lock-in so powerful? It's because the foundational frameworks of modern AI, PyTorch, TensorFlow, and JAX, are all built and heavily optimized to run on CUDA. Major algorithmic breakthroughs, like the flash attention algorithm that dramatically optimized the performance of transformer models, were written specifically for Nvidia's hardware architecture and its CUDA kernels. A competitor doesn't just need to make a faster chip. They need to convince the entire global AI community to rebuild its foundational code on a new platform. This dynamic reveals the true nature of the competition. While AMD's hardware, on paper, is often competitive with Nvidia's, its software stack is not. Developer forums are rife with complaints about ROCm being buggy, unstable, and lacking the vast library support and documentation that makes CUDA so dominant. China's challenge, therefore, is not just about fabricating a powerful piece of silicon. It is about replicating a 2-decade-old, multi-billion-dollar software ecosystem and then persuading millions of developers to abandon the industry standard. This is a far greater challenge than simply designing a chip. For years, China's AI ambitions were powered by American silicon. Its tech giants were some of Nvidia's biggest customers. That all changed on October 7, 2022. On that day, the US Department of Commerce's Bureau of Industry and Security, BIS, implemented a sweeping set of new export controls on advanced computing and semiconductor manufacturing items destined for China. This wasn't a tariff designed to make goods more expensive. It was a technological blockade designed to halt progress in its tracks. This was the public debut of what National Security Advisor Jake Sullivan called the small yard and high fence strategy. The small yard contained a very specific, narrow set of choke point technologies deemed critical to national security. In this case, it included high-performance AI chips like Nvidia's A100 and H100, the software used to design them, and the indispensable semiconductor manufacturing equipment, SME, needed to produce them. The high fence was a near-total ban on exporting these items to China. The stated goal was explicit: to counter the advancement of China's high-tech capabilities, citing national security concerns that these chips could be used for military modernization, including the development of nuclear weapons and hypersonic missiles. The initial sanctions created a frantic cat-and-mouse game. Nvidia, not wanting to lose its second-largest market, quickly engineered slightly downgraded China special chips, like the A800 and H800. These were carefully designed to deliver performance just below the legal thresholds set by the 2022 rules. Chinese tech firms stockpiled these chips, buying them up as fast as Nvidia could make them. But Washington was watching. In October 2023, the Commerce Department tightened the rules again, closing the loopholes and effectively banning these workarounds as well. The controls were also expanded to include critical components like high-bandwidth memory (HBM). The blockade extended beyond just American companies. The US engaged in a major diplomatic effort to bring its allies on board, particularly the Netherlands and Japan, which hold other critical choke points in the semiconductor supply chain. The Netherlands is home to ASML, the world's only manufacturer of extreme ultraviolet EUV lithography machines, which are absolutely essential for producing the most advanced chips. Under US pressure, the Dutch government not only restricted ASML from selling its cutting-edge EUV machines to China, but also its previous generation deep ultraviolet DUV immersion systems. In a move that sent shockwaves through the industry, they even revoked existing licenses for servicing and maintaining machines already in China, a potentially crippling blow to Chinese fabs. Washington had drawn a clear line in the silicon. The message was unambiguous. China's AI ambitions would no longer be powered by Western technology. But what if, instead of stopping China, this only forced it to build its own engine from scratch? Out of the crisis created by the sanctions, a new wave of challengers emerged, flush with state-backed capital and immense ambition. The most prominent are a trio of Shanghai-based fabless semiconductor startups, More Threads, Biren Technology, and MetaX, and they share a fascinating DNA. Many were founded and staffed by veterans of the very American companies they now seek to replace. More Threads was established in 2020 by Zhang Jianzhong, who was previously the general manager of Nvidia's entire China operation. MetaX was launched the same year by former AMD executives, including Chen Weiliang, who had served as AMD's global head of GPU product line design. Biren Technology, founded in 2019, also drew its founding talent from the ranks of Nvidia and Alibaba. This wasn't just a typical startup scene, it was a homecoming of US-trained talent, now tasked with building a domestic alternative. Fueled by Beijing's national push for technological self-sufficiency, these companies began raising staggering amounts of capital. Biren Technology secured over $900 million in funding from investors, including Ping An and state-backed SMIC. By mid-2025, the race for funding went public. More Threads and MetaX both filed for massive initial public offerings on Shanghai's tech-focused STAR market, seeking to raise a combined 12 billion yuan, or about $1.65 billion. Their IPO prospectuses laid bare the brutal cost of this quest. These companies were burning through cash at an astonishing rate, primarily on research and development. In 2024 alone, More Threads reported a loss of 1.49 billion yuan on just 438 million in revenue. MetaX lost 1.4 billion yuan on 743 million in revenue that same year. This was the necessary high-stakes gamble required to even attempt to close the gap with Nvidia. The filings also revealed a shared perspective on the geopolitical landscape. Both companies cited the US sanctions as a major risk to their development, as being placed on the US Entity List blocked them from using world-leading foundries like Taiwan's TSMC. But they also framed the restrictions as a historic opportunity. As More Threads stated in its prospectus, the sanctions have prompted Chinese firms to accelerate domestic substitution processes. This is the sanctions paradox in action. The US export controls, designed to be a chokehold, have inadvertently become the single greatest catalyst for China's domestic semiconductor industry. By cutting off the supply of foreign chips, Washington created a protected, multi-billion-dollar captive market for any viable domestic GPU startup. As one analyst noted, when countries are cut off from GPU oil, they need to find their own source, and that's exactly what China is up to. But it's a big gamble, because as we've seen in the past, not all chip startups end up making the grade. With billions in funding and a guaranteed market, the new challengers began to unveil their silicon. But the central question remained, how does it actually perform? The most visible domestic alternative to Nvidia has been Huawei's Ascend series of AI accelerators. Developed in partnership with China's top domestic foundry, SMIC, the Ascend 910C represents a significant national achievement. But a closer look reveals the scale of the challenge. Independent research from the AI lab DeepSeek, a major Chinese AI developer, suggests the Ascend 910C delivers roughly 60% of the performance of an Nvidia H100 when it comes to inference, the task of running an already trained AI model. This is an impressive feat, making it a viable, cost-effective alternative for some applications. However, for the much more computationally demanding task of AI training, Nvidia is said to maintain its undisputable lead. The gap is not just with Huawei. While startups like Biren Technology made bold claims with their initial BR100 chip, real-world performance has been hard to verify, and the company was quickly cut off from its manufacturer, TSMC, by sanctions. More Threads has launched several generations of GPUs, but its consumer-grade MTTS-80 and professional MTTS-4000 still lag significantly behind their Nvidia counterparts in raw power. A side-by-side comparison makes the technical gaps starkly clear. This table highlights the challenge. Even before being cut off from TSMC, Biren's BR100 was a generation behind the H100 in memory technology and computational power. Huawei's Ascend 910C, built on SMIC's less advanced 7nm node, shows significant compromises in performance and memory to manage power consumption. More Threads S4000 uses slower GDDR6 memory instead of the much faster high-bandwidth memory, or HBM, used in data center chips, severely limiting its bandwidth. So, if you can't build a faster chip, how do you build a faster system? Without access to ASML's state-of-the-art EUV machines, Chinese foundries like SMIC are effectively stuck on older, less dense, and less power-efficient 7nm process nodes, which are several generations behind the 4nm nodes used by TSMC for Nvidia's H100. This manufacturing gap seems insurmountable. So how do you build a cutting-edge system with yesterday's tools? The answer lies in moving up the value chain from pure fabrication to integration through a set of techniques known as advanced packaging. Instead of trying to build one single, massive, complex chip, what's known as a monolithic design, Chinese firms are focusing on a chiplet approach. They can manufacture smaller, specialized chiplets on more mature, reliable process nodes, and then package them together with extreme precision on a single base layer called a substrate. Technologies like CoWoS, or chip-on-wafer-on-substrate, allow them to connect multiple GPU cores and stacks of high-bandwidth memory so tightly that they can communicate almost as if they were on the same piece of silicon. This requires mastering complex front-end wafer manufacturing techniques like etching and deposition, giving integrated foundries like SMIC an advantage over traditional assembly and test companies. Think of it like building a high-performance engine. If you can't forge the entire engine block from a single, flawless piece of an advanced alloy, you can instead craft smaller, perfect components, pistons, cylinders, valves, and then weld them together with microscopic precision. The end result can be surprisingly powerful, and it's a strategy that China's domestic packaging firms like JCET and Tongfu Microelectronics are aggressively pursuing. This isn't just a temporary workaround, it's a fundamental strategic pivot. Unable to compete at the bleeding edge of fabrication, China is attempting to shift the point of value creation in the semiconductor supply chain to a domain it can control: packaging and integration. Here lies the great paradox of the GPU quest. By banning the sale of Nvidia's best chips, the US government has unintentionally guaranteed China's fledgling GPU makers a multi-billion-dollar market, completely sheltered from foreign competition. China's own tech giants, Baidu, Alibaba, and Tencent, collectively known as BAT, have no other choice but to buy domestic. For a time, these giants went on a frantic buying spree, stockpiling every Nvidia chip they could legally acquire, and, according to some reports, even sourcing them through intermediaries and black markets. In May 2025, Tencent's president, Martin Lau, admitted the company had a pretty strong stockpile of chips that would be enough to train its AI models for a few more generations going forward. But stockpiles don't last forever, and the demand for AI compute is growing exponentially. The pivot to domestic hardware is now undeniable and accelerating. Baidu, which developed its own Kunlun Core AI chips, is now also actively working to support domestic GPUs, like those from More Threads, for running its popular DeepSeek AI models. Alibaba Cloud, while still offering Nvidia GPUs in its data centers outside of China, is also building out its domestic infrastructure with its in-house T-Head semiconductor division. And Tencent, while leveraging its stockpile, is publicly exploring other chips from within China to fulfill its massive and growing need for AI inference. This forced adoption is nurturing what can only be described as a walled garden, a self-contained, self-reliant AI ecosystem inside China's Great Firewall. It is becoming a parallel technological universe. In this universe, domestic hardware from companies like Huawei, Threads, and MetaX is becoming the standard. This hardware runs on domestic software stacks like Huawei's Mindspore AI framework and CAN compute architecture, or Threads Musa platform. These systems are then used to train and run domestic large language models like Baidu's Ernie, Alibaba's Qwen, and Tencent's Hunyuan. Finally, these models power domestic applications that serve China's 1.4 billion people, from search engines and e-commerce platforms to the super app WeChat. It's reminiscent of the early days of the internet. While much of the world built on open standards, some companies like America Online, AOL, tried to create closed, proprietary online services. China is now being forced by geopolitics to build a national, hardware-level version of this walled garden, not by choice, but out of a state-mandated necessity for survival. Building this parallel universe is fraught with challenges. Hardware is only half the battle, and arguably the easier half. The biggest and most persistent hurdle remains the software. Nvidia's CUDA is a fortress, fortified by 2 decades of relentless development, optimization, and the loyalty of millions of developers worldwide. Chinese alternatives like Threads MUSA, MetaX's MXMACA, and Biren's BIRENSUPA are, by comparison, in their infancy. While Threads has impressively demonstrated that its GPUs can run code written for CUDA, this is likely achieved through a translation layer, which almost always comes with a performance penalty. True, native performance requires an entire ecosystem of optimized libraries and developer tools, which takes years to build. The experience of AMD's ROCm platform is a cautionary tale. Developer forums are filled with stories of frustration. It's buggy, performance is inconsistent, and often a fraction of the hardware's theoretical potential, and documentation is sparse. Chinese developers, building on even newer and less mature platforms, face the same steep uphill climb. Massive state investment is also no guarantee of success. Beijing's top-down industrial policy has been criticized by some analysts for the inefficient allocation of capital and AI chips, creating waste and redundancy. There is a significant risk of creating zombie companies that can survive indefinitely on government subsidies, but can never truly innovate or become globally competitive. Furthermore, some experts warn that this inward turn could be counterproductive. Forcing China's most advanced AI companies to use less powerful, homegrown chips will likely slow their progress in developing frontier AI models, at least in the short to medium term. The CEO of DeepSeek, one of China's most successful AI startups, admitted it bluntly. "Money has never been the problem for us. Bans on shipments of advanced chips are the problem." This highlights a fundamental trade-off China is making, sacrificing near-term progress at the absolute cutting edge for long-term resilience against sanctions. This constraint is forcing a philosophical shift. While Western AI labs have largely pursued a scaling law approach, the belief that bigger models, more data, and more GPUs will inevitably lead to better results, Chinese firms are being forced to innovate on efficiency. Tencent's leadership has publicly stated they are moving away from this belief and focusing on getting very good results from smaller, more efficient clusters. They are investing heavily in software optimization to, in their words, double the capacity of their existing GPUs. This necessity-driven focus on doing more with less could paradoxically become its own competitive advantage, positioning China as a future leader in AI efficiency even if its raw hardware performance lags. Finally, it's crucial to acknowledge that the US blockade is not, and can never be, perfectly airtight. A thriving and sophisticated black market for Nvidia chips has emerged. Reports have detailed elaborate smuggling rings using shell companies to purchase entire servers from Dell and Supermicro, which are then shipped to data centers in intermediary countries like Malaysia and Singapore to be used by Chinese firms. While this illicit flow is not nearly large enough to power China's entire AI industry, it demonstrates the extreme lengths to which companies will go to get their hands on superior hardware, and it remains a persistent leak in the high fence. So, can China replace Nvidia? The answer, like the quest itself, is complex. A simple no ignores the sheer force of political will and the torrent of capital that Beijing is deploying to solve this problem. A simple yes ignores the colossal technical and ecosystem hurdles that remain, particularly the 2-decade head start embodied by Nvidia's CUDA platform. What is clear is that US sanctions, intended as a knockout blow, have instead acted as a powerful stimulant. They have created a protected, multi-billion-dollar walled garden for a new generation of Chinese chipmakers. While these startups are attempting to close the hardware gap through clever engineering like advanced packaging, they remain years, if not a decade, behind in the all-important software war. This has forced China's tech giants into a corner, making them captive customers and partners, and in doing so, accelerating the development of a parallel, self-reliant, but for now, isolated AI technology stack. The next few years will be critical. The world will be watching for the real-world performance of the first major AI services from Baidu, Alibaba, and Tencent that run entirely on domestic GPUs. It will be watching the stock performance of More Threads and MetaX following their 2025 IPOs to see if they can deliver on their ambitious promises to investors. And finally, it will be watching Washington to see if the US tightens the screws further, or if it finds that its high fence has simply cultivated a new, determined, and unpredictable competitor. The GPU quest is more than a corporate rivalry or a technological race. It may mark the beginning of a great bifurcation, the dawn of a world with two distinct, competing, and potentially incompatible technology ecosystems. A world where the future of artificial intelligence is no longer written in a single, universal language, but in two.